Next, we will learn how to perform differentiation in polar coordinates. And let's consider the following task. Let's say we are given the curve and we want to find the equation of the tangent line at when theta is equal to pi over 3. So again, how do we understand this task? We have some sort of curve. When theta is pi over 3, we want to find the equation of this tangent line. We're going to look for the equation of the straight line in a Cartesian form, because lines are better written in Cartesian form, but the curve itself is given to us in polar coordinates. So where do we begin? Well, first we can identify the point where to look for the tangent line. So we're going to evaluate r at pi over 3. So we have 2 minus 2 cosine of pi over 3. Cosine of pi over 3 is 1/2. So we get 2 minus 1, which is 1. So this everything is happening at the point 1 comma pi over 3. But remember, this is a Cartesian, this is a polar coordinates. So let's go ahead and convert the coordinates of this point into Cartesian. So we're going to be using the conversion formula. X is equal to r times cosine theta, and y is equal to r times sine theta, and x is equal to, therefore, as 1 times cosine pi over 3, which is 1/2, and y is equal to 1 times sine of pi over 3, which is √3 over 2. So the point at which we're looking for the tangent line in xy coordinates can be expressed like this. So to find the equation of the tangent line, we're going to use the point slope formula. And to use the point slope formula, we set it up like this. And we already know that the y coordinate is √3 over 2, the x coordinate is 1/2, and the only thing we don't know is the slope. What is the slope? The slope is the derivative of the function evaluated at the point 1/2. So this is where we have a need to be able to find the slope of the tangent line of a curve given to us in polar coordinates, in polar form. Now, to answer this question, we're going to use the parameterization of the original curve. So first, let's parameterize it. So to parameterize it, we're going to use this formula that x is equal to r cosine theta and y is equal to r sine theta. But instead of using it to convert the point, we're going to use it to convert the entire equation. So instead of r, we're going to plug in 2 minus 2 cosine theta times cosine theta, and instead of r here, we're going to do the same. And now if it makes it easier for you, you can replace theta with t, but we're just going to keep it as theta here. All right, so now that we have it parameterized, the task of finding the derivative of f now becomes the same as finding dy dx and then evaluating it all when x is equal to 1/2, but x is equal to 1/2 when theta is equal to pi over 3, which is our parameter. So to find dy dx, we're actually going to use the formula for finding the derivative of a parametric equation. So we're going to take dy dt, but since we have theta as our parameter, we can express it like this. And we're kind of done, because all we need to do is differentiate the y with respect to theta. So 2 cosine theta minus 2 cosine 2 theta, and divide it all by derivative of x with respect to theta, so negative 2 sine theta minus 4 cosine theta times the negative sine theta, so it looks like this. And using the trigonometric identities, I can just rewrite this as 2 sine 2 theta, and we have to now evaluate it when theta is equal to pi over 3. So we have 2 cosine pi over 3 minus 2 cosine 2 pi over 3, all divided by negative 2 sine pi over 3 plus 2 sine 2 pi over 3. And what do we have here? We have cosine of pi over 3 is 1/2, cosine of 2 pi over 3 negative 1/2, sine of pi over 3 is negative root 3 over 2, sine is radical 3 over 2, but altogether it's negative 2 over 3, and sine of 2 pi over 3 is also root 3 over 2. So what do we have as a result? In the numerator we have 1 plus 1, which is 2, and in the denominator we have 0. So this expression is undefined, but it's undefined in a way that we have division by 0. So what's the conclusion? The conclusion that the slope doesn't exist, therefore we have a vertical tangent line. So I guess this point slope formula isn't going to work because m is undefined, but undefined just means that x is equal to 1/2. That's what that means. So the equation of the vertical line here is x equals to 1/2. Let's find just the slope of the tangent line without trying to find the equation of the tangent line for the following curve. When theta is equal to 9e. So again, the question is find the slope. We're gonna do exactly the same approach as earlier. We're going to parameterize the curve, and then we're going to find the derivative. So x of theta is equal to r, which is negative 5 ln theta times cosine of theta. Y of theta will be equal to negative 5 ln theta times sine theta. And if we're looking for the slope of the tangent line, we're looking for dy dx, which can be found as dy d theta divided by dx d theta, and we gotta do differentiation carefully. So the product rule, we're gonna have negative 5, and we're gonna have derivative of ln times sine plus ln times cosine, and the same thing with the denominator. We're gonna factor out negative 5, so we have 1 over theta times cosine plus ln theta times negative sine. The negative 5 can be reduced, and we have a simplified version of it. We can just multiply everything by theta. So we have sine theta plus theta ln theta cosine theta over cosine theta minus theta ln theta sine theta. And we simply need to evaluate this at theta 9e. So just throwing 9e there, we have sine of 9e, which is not pretty, plus 9e times ln of 9e times cosine of 9e. None of this is pretty, so I'm just going to grab a calculator and do it with a calculator. And my favorite calculator is Wolfram Alpha. So let's throw it in Wolfram Alpha and see what happens. So we're gonna have a fraction. We're gonna have sine of 9e plus 9e. I think I'm just gonna copy it. We're gonna have ln of 9e cosine of 9e, and we're gonna have very similar expression in the denominator. We're gonna have cosine of 9e. We're gonna have minus here. And we're gonna have sine of 9e here, and the final answer appears to be as 1, 2, 3, 4. I guess if I had to guess what the answer, I would have guessed 1, 2, 3, 4. I'm not sure why would have put the decimal, but this is the answer. So again, what have we accomplished? We have started with a polar curve, but we were able to compute the slope of the tangent line using our past knowledge of parametric equations and how to do calculus with parametric equations. So one last example. Let's consider the following curve, and let's identify all horizontal tangent lines. So asking for horizontal tangent lines, that's basically asking to identify all the points where the slope is equal to 0. And first we're going to identify first we're going to parameterize it. And then we're going to find the slope. And we're basically doing the same steps, finding the slope as before. The hardest part here is to differentiate these products. Let's see, we have dy d theta, that will be the product rule, so negative 3e to the 3 theta sine theta plus e to the negative 3 theta cosine theta. And we're going to have same thing here, negative 3 e to the negative 3 theta cosine theta minus e to the negative 3 theta sine theta. You can see how e to the negative 3 theta is gone. So we have negative 3 sine theta plus cosine theta. We have negative 3 cosine theta minus sine theta. And we're looking for the horizontal tangent line, and the horizontal tangent line happens when the slope is equal to 0. And the slope is equal to 0 only when the numerator is equal to 0. So solving this equation gives us the following. So it will happen when theta is equal to arctan on 1/3 plus pi n. So there will be infinitely many points where this curve will have a horizontal tangent line. So let's see what it looks like in Desmos. So here's the equation of this polar curve. Not impressed with this as theta. What's going on here? Let's allow theta to go negative, and that's where we see where everything is happening. But still, why is there infinitely many tangent points where it has a horizontal tangent line? Let's see. We're going to parameterize it first. So e to the negative 3t times cosine t, comma, e to the power negative 3t times sine t. So we get the same thing. Let's go from negative 100 pi to 100 pi. I would like to be able to visualize this. So let's try to replace parameter t with a and trace this point. So what's going on here? So as a increases, we just hit to the 0. And let's see. seems like as A gets bigger, the point gets closer and closer to the origin. But why do we have so many tangent lines? So let's see. When theta is equal to arctan of 1/3, it's arctan of 1/3. So when we make A equals arctan of 1/3, this is the point where we get the tangent line, the horizontal tangent line. And in theory, so let's see what happens when we add pi or 2 pi. Interesting. So there is something going on here at we have this. Oh, this is very interesting. So I went 6 pi. Hold on, let's go back up. Let's add pi. Where am I with just pi? All right, there you go. So this is my other horizontal tangent line, and if as I add another pi, it's gonna take me over here. This is like an infinite spiral that goes towards the pole. This is a pretty interesting picture. So this is another tangent line. So we have found all the points where the graph has a tangent line, and we actually learned something about the graph, which would be really hard to learn just by looking at the graph of the curve. Oh my god. So if you what looked to be, I guess it keeps spiraling like inside and outward, which is pretty interesting behavior. Anyway, this is how we do derivatives with polar in polar coordinates.